Popov. Today, he's a TSVP visitor until the end of this month, I think. Yeah. He obtained a PhD from Princeton and then did a postdoc at NYU, New York University, and now a research assistant professor at Simons Center for Geometry and Physics. He's wearing a t-shirt at Stony Brook University. And then, so his research is quite wide, in my opinion, for kind of within physics. In general, he thinks about QFT encompassing high energy theoretical physics, quantum gravity, and also fullness matter physics. He thinks about large N limits of certain models like matrix and tensor models in connection to quantum many-body systems, and also conformal theories. And also thinks about, I think, problems in the zeta space. And then recently, I think, working on also QCD, quantum thermodynamics problems as well. So today he will tell us about entropic order. Yeah, please, thank you.
Okay, thank you very much for the very kind introduction. So, and also I would like to thank people from OIST for this kind of very wonderful program. TSVP to visit OIST and from every point from the world. And I would like to thank TSVP admin teams who helped me a lot with getting all documents to visit here. So I will talk about my two recent papers. Oops, sorry. This one. So we published one paper December last year, almost a year ago, with Dr. 𝐒𝐤𝐞𝐵, who is a permanent professor at Simons Center for Geometry and Physics, where we studied some large N vector models and found some peculiar properties where some low temperature phase was able to sustain to up to very high temperatures. And based on our observation, together with Andrew Lucas, who is professor at the University of Colorado Boulder, and two of his students, 𝐒𝐤𝐞𝐵 and Huang, we managed to generalize these ideas to some other lattice model. And 8 months ago, we published another paper, and that was recently accepted to Nature Communications. And I decided to name my talk after this last paper that we called entropic order. At first glance, it sounds a little bit mysterious, and it was done on purpose because of people usually like mysteries. And second of all, it sounds very strange because of usually when we talk about entropy, it's something that is opposed to order. Entropy means that we have a lot of states and hence disorder. So it sounds a little bit like oxymoron, like a warm snow. But as I will try to explain to you later, it's directly connected to this oxymoron of warm snow. So let me give you another title that less mysterious, but conveys the main idea that we are trying to find a high temperature persistent spontaneous symmetry breaking. And even though now it's clear what I want to do, that I want to find some systems that exhibit spontaneous symmetry breaking and that persist at high temperature, still it's not clear what is spontaneous symmetry breaking and why we should not expect it at high temperatures. And to finally give you some very low-level questions that I want to answer is whether it's possible for Okinawa to have permanent snow, so to build some very ski resort and enjoy it together with the nice beaches. So you see that it seems quite strange how it's related to this question of high temperature persistent spontaneous symmetry breaking, but I will try to explain to you how these all questions are related and how to the answer to all of these questions is entropic. So let me start now from some motivation, from some introduction to this question. So from the dawn of human civilization and philosophy, people were trying to understand the nature of matter. What are the fundamental constituents of matter and what phases of matter exist? Now we know the answer to the first part of the question, that we know that matter consists of atoms and molecules. Atoms and molecules consist of quarks, leptons, and other stuff, interesting stuff. And that explains 5% of observable universe. You think that 5% is a very small number, but actually it explains all observable universe that we see present in this room, or on the Earth, on the solar system. The other stuff is dark matter and dark energy, and that we still don't know, but doesn't affect our everyday life. So we almost satisfies the question, what's the constituents of matter? Now the second question is like what are different, how to classify different states of matter. So, for instance, if we take water that we know consists of H2O molecules, they interact exactly the same way, whether it's under high pressure or high temperature. But nonetheless, they somehow exist in completely different states. That you take water, cool it down significantly enough, you will see that it turns into ice. Completely different behavior from the water. And people try to understand how to rigorously differentiate these different states of matter from the dawn of human civilization. It's not just a simple answer that it's a different by different properties. Because of, for instance, if you take water and drastically change pressure and temperature, it will behave completely different points of this phase diagram. So we need to find some fundamental principles that differentiate us ice from water. And there was different attempts how to answer this question depending on the dominant philosophy at that time. So, for instance, in ancient Greece, people tried to connect different phases of matter to so-called 4 fundamental elements: fire, air, water, and earth. And even though this classification nicely fit into our everyday observation, it was not very rigorous enough, because it doesn't tell us how to classify if we discover some new phase of matter. And it was, roughly speaking, based on the idea that we can just explore the universe without using any experiments. So it was just projection of subjective beliefs on the observable world. After that, in the 15th century, when people start doing some experiments, they try to contest these ideas with the observable experiments, and they somehow managed to create much more sophisticated classification system, but it still was just improvement of the Pythagorean of ancient Greece classification of matter. So it was not, so they didn't discover the fundamental reason how to classify different states of matter. Later on, by the end of 19th century, people did some sort of research and decided to do some sort of decision tree to differentiate different states of matter. But nonetheless, still people did not understand how to distinguish 2 different states of matter. How, if I encounter some new matter, how do I distinguish different states? And it was an open question until Pierre Curie discovered spontaneous magnetization. So he did the following. He didn't bother with the question how to classify different states of matter. He just wanted to understand what happens if you take a piece of copper and significantly cool it down. For instance, you can take a piece of copper. Let's make a sphere out of it. Let's study what happens once you lower the temperature. He found out that when temperature reaches some particular value, namely 77 kelvins or minus 200 Celsius, suddenly this piece of metal starts to exhibit spontaneous magnetization. So if you take a compass and bring next to this piece of copper, the compass will direct it. What is happening there, roughly speaking, on the high level, is that we can represent our piece of copper as a bunch of spins that exist in the body of this piece of metal. At high temperatures, these spins are completely Sorry, so there is a question. Of course, if you have any questions, please interrupt me and I will be happy to answer. So at temperature higher than critical temperatures, these magnets are completely disordered and there is no net magnetization. So this magnetization is equal to 0, as you can see from this plot. But as soon as you go below this temperature TC, critical temperature or Curie temperature, these spins decide to align with itself, as you can see from this plot, and they pick some direction. You see that here it follows specific law. It's like
Online, is there a question? Is there a way to mute?
Yeah, they are muted now.
Thank you.
Okay, so it follows the law T minus TC to the power 1/2. So it was a big question to explain this power law 1/2 and explain why is it happening. Because of at first glance, it seems to be very bizarre that we believe that the law of physics governing this piece of copper should be symmetric, meaning that if I take this piece of copper and rotate it by 20 degrees around some axis, it should be described by exactly the same physics, but somehow if I introduce this color perturbation, it doesn't have any directions, I break somehow spontaneously my rotational symmetry. So even though, just to reinstate it, even though I have a symmetry and all directions are preferable, somehow my piece of metal at temperatures lower than Tc breaks this symmetry and wants to direct somehow. It caused a lot of debates, and Pierre Curie thought that maybe somehow his experiments was flawed fundamentally, because he believes that the symmetry could only caused by disymmetric law of physics. And he believes that maybe somehow he couldn't manage to completely shield the external perturbations. But nonetheless, all of his attempt to shield this external perturbation failed. He always observed this magnetization. Yeah. Later on, Pierre Weiss proposed explanation of this phenomena by stating that this direction is much more energetically preferable than this one. And for that, magnet would prefer to break its symmetry and to direct somewhere. Another interesting observation that Pierre Curie did is that, according to this old ideas how to classify different phases of matter, when they experience spontaneous magnetization, the system experiences phase transition. Namely, if you study some heat capacitance, conductivity, and so on at this different region of this temperature range, you will see that it belongs to different phases of matter. Hence, it led to ideas, maybe we can connect phase transitions to spontaneous symmetry breaking. And this idea was sharply stated by Lev Davidovich Landau, famous Russian theoretical physicist, who stated that to each symmetry breaking pattern, we will assign a state. So let me unpack it. So assume that we have some symmetry, some material, some theory, and assume that it has some fundamental symmetry. For instance, if you take the water, it's a symmetry of shift symmetry, that if I write down the direction between H2O molecules, that depends on this relative distance. There is no fundamental shift difference between other shifts. If I study this model, they have fundamental symmetries as of 3 symmetry. So now we study whether the symmetry is broken or respected as parameter of as a function of its external parameters, say temperature and pressure, and maybe magnetic field, and see what symmetry is preserved or broken. And if given symmetries are preserved while the others are broken, we will see that it corresponds to a symmetry broken pattern. So, for instance, if you take water at high temperature, the symmetry is respected. There is no symmetry breaking pattern. That all symmetry is symmetry of the series minus symmetry of the state, and this can represent one state of matter. If now I will cool significantly down, some of my symmetries, namely shift symmetries, get broken to a discrete subgroup. You see that in liquid I can shift my system by any distance, and it will be correspond to exactly the same phase of matter. But if I shift solid by some particular number that is not integer number of this lattice shift, then it will correspond to a different sort, not related to the original sort. So, that's why we say that in this case our symmetry got broken to a discrete subgroup, and this will correspond to a different symmetry breaking pattern. So we will now associate to each, if we have some model, we will study the symmetry breaking pattern as a function of its parameters, say pressure and temperature, and assign to different symmetry breaking pattern a new phase of this particular model. It was the original idea of Landau. That's called Landau, is now known like Landau theory of phase transitions. Based on that, he wrote some phenomenological theory describing the phase transition and managed to successfully reproduce, for instance, this plot that he managed to show that this is precisely behaves like the root of T minus Tc. But actually now we know that there is some small correction to this power law that could be taken, that comes from the thermal and quantum fluctuation. So this Landau paradigm was very nice, and as you can see, a lot of newly found matter and phases of it nicely fit into this classification. even some strange phase transitions like confinement-deconfinement transitions that I forgot to add here. Nicely fit into this paradigm, but you must generalize the idea of asymmetry. So now we know what is different phases of matter. We just assign different spontaneous symmetry breaking patterns to different states of matter and see how the spontaneous symmetry breaking patterns depends on external parameters, say temperature or pressure. And if our symmetry breaking pattern changes, we say that we have a phase transition. Okay. So now we know how to differentiate ice and water. We just studied whether symmetries are broken or not. Now the question is what we should expect, what kind of phases or symmetry breaking patterns we should expect as a function of external parameters. These parameters could be rather different, but ubiquitously it's only temperature. So from now on, I will concentrate on the question what we expect, whether symmetries are expected to be respected or broken at high or low temperatures. To answer on this question, naively, I will follow again Lev Davidovich Landau, especially this paper, who made the following observation. Assumes that I want to study some correlation function, namely some observable odd, and study the function of temperature. Then from the law of physics, we know that to compute this correlation function or one-point function, I just need to average this observable odd with respect to all parameters, all configurations of my theory, by taking into account the density of states, namely this factor e to the power of SE, where S is called sometimes entropy, and multiply with the probability of appearing in this given state. So I multiplied by this Boltzmann factor minus E over T. And now I just need to study this O as a function of temperature. To make connection to the previous question about symmetry breaking, let me consider some potential. I'll consider this double well potential. You see that it's symmetric, that if I map M to minus M, it will go to itself. It has peculiar properties that it has 3 stationary points, this one, and this one. Only one is actually respects the symmetry, only this one, while this one disrespects the symmetry because of under the action of the symmetry, this guy will map to this guy and this map will this guy. But the big advantage of these two ground states is that they has much more significantly lower energy than this one, symmetric one. Hence, if I study limit of low temperature when T goes to 0, my system will try to hang out most of the time here or here. So let us do this. So I will take my particle and put initially around one of these vacuum states. And now I will study some thermal properties of the system. And I will see that, for instance, if I study magnetization, most of the time this magnetization is not equal to 0 and equal to minus A. It happens because of, even though the thermal fluctuations could be strong enough and will force my particle to go here, that happens with a very low probability. I need to wait maybe after the death of Sun, the universe, to see that my particle finally go from this vacuum universe to this vacuum universe. Hence, I expect at low temperatures that my symmetry must get broken. And to describe what's happening here, I just need to study what's happening around this. As I increase temperature, this cost of this thermal fluctuations goes down. Roughly speaking, this factor becomes less and less important. What becomes more important is the entropy factor. And my system will try to explore most of the universe. And because of that, effectively, my parameter O that I will measure, for instance, M, will get effectively average, and I will see 0 on average. Hence, I will have the restoration of my order parameter of symmetry. So from this argument, let's call it energetic order, I expect that at low temperatures I must have an ordered state, and high temperatures I must have a disordered state. It seems that from this point of view, from our everyday experience, it nicely fit in all of our experiments. For instance, in the case of water, if I heat it up ice, it will turn into liquid. If I take this magnet, if I heat it up, it again loses spontaneous magnetization. So it seems nicely fit, but actually nature provides some interesting counterexamples to this general argument. The first one is quite simple. It's called Rochel's salt. It's some medicine that you can buy on Amazon. For instance, I took this picture from Amazon. I will not tell you how people use it in real life. But it has an interesting property. It is found to be in medicine. It experiences spontaneous magnetization as piece of copper, but it's experienced spontaneous magnetization not at low temperature, but some intermediate region between -20 Celsius up to 35 Celsius. So you see that the order of phases is switch. You start at low temperatures with the ordered state. With this ordered state, you heat it up, you get the ordered state, but miracle does not happen. It comes back to the disordered state. So it's a very simple example. And the other example is much more interesting. And you cannot easily get it from Amazon. You need something much more complicated. Maybe you need to go to the moon or something like that. It's all called 𝐒𝐻𝐿𝐿 effect. That people, when they found helium-3, they made some experiments. They found very interesting observation. Namely, if you take helium-3, put under very high pressure, 10 to the 5 atmospheres, and study the phase diagram, at first glance, it looks very simple. You go to one critical temperature, and the liquid helium-3 becomes solid. So you might say that it's quite the same as in the case of water-ice phase transition. Actually, what is happening here is that latent heat here becomes negative. So it means that if you take hot coffee and decide to cool it down, and you take ice cubes of helium-3 and drop it into your hot coffee, instead of cooling it down, it will heat it up. So it means that when it cools down, instead of absorbing energy from surrounding, releasing energy to surrounding world, it absorbs it. Because of that, it's now it's very useful for experience, because of this way you can reach very extremely low temperatures. But it was a big question how to explain this negative latent heat, and actually it was explained by Pomeranchuk, another Soviet physicist, who pointed out that entropy of the solid state here is actually higher than the entropy of the liquid state. I took this picture from this original paper by Pomeranchuk. As you see, they have TV, it means solid, and 𝐒𝐩𝐞 means liquid. You see that entropy of the liquid phase is lower than the liquid of the solid state. That is completely different from the observations that we made before, that the entropy of the disordered state is higher than the entropy of the ordered state. And because of that, you have this very strange behavior.
Sorry, question here. Naively seems like if you have an upper bound on the temperature or the energy states it can take, you can still have like your system getting more ordered as the temperature is getting higher. Is something like that happening here?
I don't know.
So for example, if you have an upper bound on the energy stage, like I can, like so given a system, the entropy is like how many configurations it can have. And more I heat it up, it's going to an upper bound. So it's ordered, but it's at a higher temperature. Something like that, what happens if you have negative temperatures? Is something like that happening here as well?
I didn't understand what you said, but yeah, something like here is happening here. That that if you study what's happening here, when it becomes solid, it gets additional vibrational degrees of freedom. And roughly speaking, taking into account this vibrational degrees of freedom, they contribute another entropy. And because of that, entropy of the solid state becomes bigger than the entropy of the disordered state. Roughly speaking, what's happening here, allowing you to have order, increases your entropy somehow, miraculously. Completely defying this usual notion that order is opposite to disorder. Did I manage to answer your question?
Yeah,
Okay. So to proceed, let us do some to understand where the Landau argument breaks down in these two examples. Let us try to make this argument more sharp, because as soon as we understand what are the crucial parts of this argument, we can easily break them and construct counterexamples to Landau argument. So for that, let me just quickly remind you what is potential symmetry breaking, why we expect it to happen in classical mechanics, why I expect that it doesn't happen in quantum mechanics, and why it reappears in quantum physics. So for that, let me consider the following simple problem. I will take Mexican head potential as umbrella, And I will study what's happening if I put a particle, a classical particle of this potential. Then we'll study ground state of the system. There exists infinite plus one ground states here. Namely, you can put a particle in any point in the rim of the sombrero head, or you can put it on the top of the sombrero head. After that, you might notice that if I put this particle here, it will respect my symmetry. I can rotate my sombrero, and this particle will get mapped back to itself. But this highly unstable system, well, because of any small perturbation, a typhoon, a tremor, just me passing by, will immediately force this particle to go to much more stable vacuum state. But the price that it pays that it now must break its symmetry. And since classical mechanics, when we take some particle, we must assign definitely where it's located, we get breaking of spatial symmetry breaking, that we must point out that our particle located exactly at this point of sombrero, and if I measure some observables, I will immediately see that my symmetry got broken. But if I take into account quantum mechanical behavior of my particle, here is just like I drew it like a wave here, I will notice immediately that if I put my particle here, it starts to quantum tunnel between different vacuum states of this rim of this sombrero. And because of that, if I wait long enough, all my observables will get averaged with respect to all vacuum states of the sombrero. So even though classical particle decided to go to this low value with low energy, quantum fluctuations effectively average my system, and I will see that my symmetry goes restored. If I want to put it in much more solid ground, I can say that by the Perron-Frenebus theorem, we know that ground state quantum mechanics must be unique. And because of if my Hamiltonian computes with some symmetry G, it means that this system must be invariant under the action of the symmetry G. But we see that the main reason why the symmetry got restored is that the appearance of non-zero quantum transition probability between two different vacuum states. Hence, I might get again my spontaneous symmetry breaking quantum mechanics if I somehow suppress this quantum probability, these transition probabilities. To do that, let me study the following pathological system. I will just study again the double level potentials that I studied before for the Landau argument, but now I will study the quantum problem here. If I study the spectrum, I will see that it's non-degenerate. To each energy state in this potential, there exists exactly one wave function. But as soon as I increase the depth of this potential, so I will send lambda to infinity, I will see that energy decide to pair with each other. So there will exist again discrete spectrum, but the spectrum will organize in pairs that are exponentially close to each other. And if I take strictly limit lambda goes to infinity, I will see that energy spectrum will just coincide that E plus I will be equal to E minus I, and the wave functions will be completely localized on the left or on the right. And in this particular limit, I will see that if I will try to measure some observables, say some strings of X and P here, I will see that matrix element between these two universes is just equal to 0. So what can I say? My system has some algebra of observables, and my Hilbert space actually now is not a reducible representation of this algebra of observables, but a reducible representation. My system got split into two halves, in the right universe and the left universe. And if, again, I will start some experiments, I will put my particle here, it will always be in the right half of this thought experiment, and I will always see that my system is decided to break its symmetry. You might oppose to me and say that maybe instead of studying such a system, I should study such a statistical mixture that I create half particles on the left and half particles on the right and average it. But after that, I will see that here happens exactly the same as happened in the case of the classical situation. If I add a small perturbation, it breaks my symmetry. My particle will decide to go either all to the left or to the right. Hence, I must say that I'm not allowed anymore to something to create statistical mixtures. I'm allowed only to study one of the so-called extremal states. So we see that we have this potential in quantum mechanics, and it happens because of our transition probability between two universes got efficiently suppressed. And after that, you clearly see the difference in potential symmetry breaking and just simply double degeneracy. You could have thought from these pictures, maybe potential symmetry breaking means that I have a lot of ground states with exactly the same energy. To be honest, it's something a little bit more deep, because of, for instance, I could have considered just a spin one half particle in zero magnetic field. It has degenerate spectrum because of all spin down will have exactly the same energy. But in this case, the algebra of local observables, namely Pauli matrices, are acting irreducible in my Hilbert space, and hence I don't have decomposition of my Hilbert space into these left and right universes. So main thing here is that my, roughly speaking, my algebra of observables, my algebra of all operators, of all measurements that I can conduct in my system, cannot map me from one universe to another universe. So this will be my kind of definition of potential symmetry breaking. And now with this knowledge, I can extend it to quantum field theory. So we just need to suppress somehow quantum transition probability between these two universes. It could be done in two ways. It could be done either by suppressing probability or just considering a large number of such systems. So for instance, if I take a coin and decide to toss it, probability that it will go up or down 1/2. But if I decided to toss a million coins, probability that they will go all up or all down is exponentially small. Hence, if I consider quantum field theory, in quantum field theory is just normal than the quantum mechanics initial system with infinite number of degrees of freedom. So roughly speaking, you can imagine that I have such potential at each point of my space-time. So it's roughly speaking expressed here. Now we'll have again the suppression of my transition probabilities between two universes, but it comes not from the large coupling constant, it comes now from the large volume limit here. And if I take now limit v goes to infinity, I will immediately see again that my algebra of observables is got split into two universes. Roughly speaking, what you can say here is that if I do some local measurement, like here, I cannot rotate all spins at the same time. It will take infinite amount of energy for me to take, because of now I have to rotate spin at each point of my space-time, and it takes a lot of effort. You will get tired before you will be able to rotate. And from that, we can immediately say that what's spontaneous symmetry breaking, and to somehow resolve situations that I can create such a statistical mixture and say that there is no spontaneous symmetry breaking, I need to somehow give some tests or criteria for the spontaneous symmetry breaking. There is two different definitions for that, how to test it. One is by Bogolyubov and the other by Royal. I will follow Mr. Bogolyubov, who stated precisely exactly what we have said before, that I just need to study whether my system is stable under small perturbations or not. So Bogolyubov says that if my density matrix thing that describes my system is stable under small perturbation, that if I have small perturbation and this limit exists and smooth and doesn't depend how you take it, then you don't have spontaneous symmetry breaking. If it does depend how you take this limit, then you have spontaneous symmetry breaking. For instance, here I could have introduced the potential Hx. If h more than 0, I will see that when sending h to 0, it goes to rho plus. If h less than 0, it will go to rho minus. Okay, so now I hope that I managed to convey you what is spontaneous symmetry breaking, how it's different from just double degeneracy spectrum. It's something much more deep. Double degeneracy just follow from this much more deep argument and give you some tests how to check whether I have spontaneous symmetry breaking or not. So based on this, now we can prove some theorems. Namely, I will now prove you that if I will heat it up my system strong enough, then it must restore its symmetry. It was proven by Robert Dobrushin, who was a Russian probabilist mathematician, a student of 𝐒𝐤𝐿, who proves the following statement. Also, sometimes you can hear that it's called Gibbs uniqueness theorem. It's actually exactly the same as Dobrushin's theorem, but it depends whether you come from. If you come from Russia, you call it Dobrushin's theorem. If you come from the United States, you call it Gibbs uniqueness theorem, even though Gibbs doesn't have anything to do with it. So I don't know why it's called like that. So Dobrushin managed to prove the following. Assumes that you have some model whose local Hilbert space is finite dimension. For instance, if I take a lattice system, so if I take some lattice and put spin 1/2 at each side of this lattice, and if you cut out some local small thing out of this lattice, I will see that my Hilbert space is finite dimensional. So, roughly speaking, means that at each side there is finite dimensional Hilbert space. After that, if you assume that your interaction is local, so it interacts only small amount, entangles locally, this Hilbert spaces, then you can prove that this thing e to the minus ht, this Gibbs probabilities could be nicely expanded in the following series. You might think it's kind of strange because of what's the definition exponent, but rather not by this sum. But he managed to prove that this series convergent has finite radius convergence for T less bigger than T star, and does not depend on, no, smoothly depends on the parameters of your Hamiltonian. Then, using the criteria of Bogolyubov, I can study perturbation of my Hamiltonian by the small epsilon b. Because of T star smoothly depends on this epsilon, I can expect now that this convergence, this analytic expression is correct, is uniform, and so on. And hence, I can take study what's happening with each term in this series, and I will see that this term is the same. The series actually nicely converges to this H, and hence it will converge to this original non-perturbed density matrix. So from this, and from Bogolyubov definition of this potential breaking, I must conclude that for temperatures bigger than T star, I don't have spontaneous symmetry breaking, and if I compute some observables that are out under the symmetry, I will get that they are equal to zero. Hence, from that we must conclude that we must have restoration of symmetry. And mathematician must be happy because of they prove some very fundamental theorem here. This potential symmetry breaking cannot exist at large temperature. Physics, yes?
Sorry, is there any restriction on the type of lattice you need to have for this? And for any lattice?
Any lattice, I will show you that there was a very important loophole here.
Is there a alternating sign in that series, or is it because it's?
Oh yes, of course. It's alternating sign. Sorry. The mass. The only thing that you should care about that is just it has such convergence, expansion, and conversion from the everything.
I see.
So we must be very unhappy because of it means that, for instance, we cannot have low temperature phases at high temperature. But as I just said to you, there was a very important assumption here that we assume that locally there exists finite dimensional Hilbert space. And for a lot of spin models that people like to study, it's true. Because for instance, in an Ising model where you put a spin 1/2 at each side, it of course satisfied. But actually, as we know from quantum mechanics 101, that's definitely not true. For instance, if I put here not a spin 1/2 variable, but a Rydberg atom, I will immediately see that my Hilbert space at each point becomes infinite dimensional. So from as a studying for toy models is a very good theorem and good assumption. But if you want to study real life setups, you must actually try to see what's happening if you assume that it has finite infinite dimensional Hilbert space.
I have a comment.
Yes.
It seems to me that you're also assuming that the temperature is positive.
Of course, I will always assume the temperature.
Which means that the entropy always increases with the energy,
Yes.
which is not always the case. case.
Yes.
There are examples where
Yes.
if it's no monotonic, I mean, also in the easing model. it's not-
Yes.
So
Yes,
that's
but-
another way where you can.
Yes, but it's finite dimensional. Within dimensional, it can go far beyond.
Well, I mean, you can construct a model in which the entropy is not.
Yes,
does
but
not
here
fall.
it's just like I assume also I take infinite volume limit first.
Yeah, I wanted to mention that's another way where
Yes.
that theorem doesn't say you.
Yes. So here it was an assumption that if it was finite dimensional Hilbert space, it's just like definition of expansion. The main thing here is that you managed to prove it for infinite lattices. Okay, you can ask me later questions. So now, instead of just doing some abstract ideas, let me just go direct to some models where I can immediately see the Stony symmetry breaking occurs at very high temperatures. For that, I will consider again Ising model. At each side, I have variable sigma I, sigma j. Adjacent lattices sizes interact with each other. But now I will add an additional bosonic degrees of freedom, Nij. That controls the strength of interaction between the sigma I and sigma j. And this Nij will not be bounded. It will go from 0 to plus infinity here. And now my Hamiltonian will have the following form. I'm sorry, I made a small typo here. There should be instead of plus, it should be 1 here. Now, I will later explain to you why it's spotted. Now, let me sum over this n. At first glance, it seems like a very complicated model. How can I solve it? But actually, this could be very easily solved. But that I noticed that I can sum over all possible n's here and each link here. And that will just modify my Hamiltonian. Now this part of the Hamiltonian looks exactly like usual Ising model here, minus 1 over T effective sigma and sigma j. But now instead of the temperatures that you set up by some external thermostat, there will come with some effective temperatures that depends on these parameters A, B, that comes here, and some true temperature T. And now I can study how does this temperature looks like as a function of real temperature T. And I will see that something magical happens in this particular model, that this effective temperature actually is less than 2 divided by log A plus B divided by A minus B. And now, if I pick this temperature, this particular number less than critical temperature for my usual Ising model, for instance, in 2D it was known from exact solution by Ansager, then the spins will always be magnetized. They will always prefer to go in the one direction. Let me explain qualitatively what is happening. Because of here is plus is equal to minus, you see that if sigma I and sigma j is equal to 1, then there is no cost for adding Nij at each link. And then for Nij, roughly speaking, it's much more preferable to have sigma I and sigma j ordered. Because of that way, you can open up new degrees of freedom. So if I remind you about Pomeranchuk effect, here when we have ordered states sigma I, sigma j, we have opened a new kind of vibration of new value of degrees of freedom that could be easily filled, and they create infinite amount of them. And because of that, for n, it would be much more nicer to create some fake temperature for sigma I, sigma j, where they will decide to get in the ordered state. So we see from that thing that as a proof of concept that we can have high temperature magnetization. Just the only thing you need to add infinite number of degrees of freedom at each side. And if you want to align it back to the Dobrushin theorem, I can just say that if now I will constrain Nij to go from 0 to some large big number, I will see that it repeats the same phase diagram as in the case of Rochelle's salt. Low temperature, oh, no, not Rochelle's salt, it will be the other model. That at high temperature, but it will be exponentially large temperature, it will go back to the disordered state. So nonetheless, even though Nij was now finite and we have back the phase transition temperature, it become exponentially large. But this is where we can somehow increase this effective transition temperature by 1 to have more and more degrees of freedom. Now, yes?
Naively, like maybe I missed it, but I don't think you changed any symmetry of the system in this when you just switched from four.
No, there is sigma.
It's the same Z2 symmetry.
Yes, it's same Z2 symmetry, but now it persists very high temperature. Yeah, thank you. I forgot to mention that there is U2 symmetry, but nothing to minus sigma G. But now you might a little bit get confused. How can I create such a system? And this Nij in some sense blind with respect to this C2 symmetry. Can I find some other interesting models that doesn't require this additional Nij? And I will clearly see that it acts trivially on all degrees of freedom. So we decided we come up with an interesting model, some generalization of lattice boson gas that was introduced by Li Yang, where they study some other problems. They study the problem extensions. So they propose the following model. You take your lattice, but now instead of sigma variables, it takes value plus or minus 1, you just say whether it's occupied or unoccupied. And after that, you introduce the following Hamiltonian. So you introduce the chemical potential for the number of particles, and you introduce repulsion potential that tells you that if those things are, that prevents two sides to get occupied at the same time. That thing obeys the Brushin theorem. It has finite dimensional Hilbert space locally, and at low temperatures you will see spontaneous symmetry breaking. You have the appearance of this checkerboard pattern, and you clearly see that it breaks Z2 symmetry because of you need to pick whether this particular side black or white, or after speaking, I can shift it by one lattice step, or if you heat it up, it will go to this lattice gas where these black and white cells are distributed randomly and gets average on average. But now let me modify this problem a little bit. Now I will say that first of all, this Ni is not binary, but it takes any integer number, goes from 0 to infinity, and I will flip the sign to make this theory much more, to make this model a little bit more sensible. So I will get the following simple model. So again, I will introduce chemical potential to the particles, and I introduce repulsion potential between two adjacent cells. But I will raise it to some power of A. If A is equal to 1, the conclusion of my next slide will be true, but it requires much more fine-tuning there. For A more than 1, you will immediately see that now we will have high temperature spontaneous symmetry breaking. Yeah. So to show you that I will do two things, I will do some estimations, and I will show you some Monte Carlo simulations. So while this thing gets thermalized, I will explain to you why checkerboard phase wins at the large temperatures. So assume that I will study checkerboard phase and see how much does it contribute to my partition function. So we have the following thing. Each black dot corresponds to there is no things. Yellow dot corresponds to this could be occupied. Because of this pattern, my interaction term doesn't play any role here. You can forget about that. And then it means that at each yellow side, I can add independently as much as possible particles. Then at each yellow side, there could be of the order T particles. And because of they're distributed randomly, I will have T to the power of occupied side states. And this, roughly speaking, will give me an estimate of the contribution to my partition function. So T is the number of particles that I expect on average at each yellow side. L squared of 2 is the number of my yellow particles. Now, if I study gaseous phase like this one, I will see that now I have to take into account this constraint coming from the interaction term. And because of that, at each side, there is no T, but T to the power 1 over 2A particle sides. But now I expect that all of them can get occupied. Therefore, I get the following estimation of the contribution of my gas phase to the partition function, like this one. Now you see that if A more than 1, then this contribution becomes exponentially small in comparison to this contribution. And therefore, I must expect that at large temperatures, my checkerboard phase must win and must see the spontaneous symmetry breaking. And indeed, I forgot to put here labels that it was done for temperature like high enough, like 10 Kelvin. This one was done for 0 Kelvin or 0.1 Kelvin. And you see that the order of the phases switch. Now we have that at high temperature, we have spontaneous symmetry breaking. You might ask me a question about A is equal to 1. This requires a little bit more computation, but still it exhibits the same property. This is Monte Carlo simulation for it. You see that here, because of this tension, that this is approximately equal to this will take almost forever to get thermalized to this checkerboard state at high temperatures. So I think I managed to persuade you that by allowing order to be conveyed by entropy factor, not by the energetic factor. So here we have that, just to reinstate it, here we win because of at each shallow set we can have a lot of states in comparison to the Gaussian state because of these estimates. So now maybe using these ideas we can construct some models where we have high temperature superconductivity. Because of originally, like the main practical motivation to study this thing, it's not like making some funny persistence nodes that can survive on Okinawa or the magnets that will not get demagnetized because of you put them next to a motor. Is to create high temperature superconductivity. And for that, let me consider the following model here. You can just regard it as a usual unbound Ginsburg potential. So there is like usual my electromagnetic interaction. Field psi describing condensate of the Cooper pairs that have some charge Q. And there is additionally some fields phi I that could be thought as some phonon existing in this material. But now phonons and this Cooper pair condensate interact in some funny way, like through this potential. Roughly speaking, what it does is that it forces psi squared to be equal to phi I squared. Now I can solve this model in the mean field approximation or Hartree-Fock approximation, and I will see that first of all, fields phi I gets the following mass sigma, and to get to the solution of this Hartree-Fock approximation, I must set this thing to 0. I hide a lot of details under the rug. If you want, I can explain you much better what is done here, but you must see this just a mass sigma, and I must set this to 0 here. And because of I setting mass to 0, I immediately see that psi must get condensed and equal to this number. And because of its sum of two positive numbers, I immediately get that psi must be non-zero. And hence, I see that my system here spontaneously breaks U1 symmetry psi, gets non-zero wave, and becomes Higgs. So I will always have the condensate of my Cooper pair, and hence I will always have a superconducting phase. Small caveat with the use of this approximation that is going to be complete. So it will be much more nicer to study some lattice approximation and check whether this high temperature phase actually survives up to very high temperatures. And again, just to reinstate you how it's connected to my own previous considerations, that I will show you the entropy of the disordered state is actually bigger than the entropy of the ordered state. It will be done by computing the thermal free energy of this Hartree-Fock approximation. Sigma here is the mass of my field, and you see that if I set sigma to 0, the entropy of my thing will be bigger than the entropy without this massive field. So speaking, it happens because when sigma is equal to 0, field phi can fluctuate much more wildly when sigma is not equal to 0. And you see that setting sigma to 0 upside on 0, it immediately gives me very high entropy. And because of that, if I randomly choose some state, it most likely will be in this state. And hence, I will have this spontaneous breaking of this U1 state. So it's again the same mechanism that you can kind of see in the Pomeranchuk effect in these lattices models. Okay, so it finally brings me to the end of my talk. So I hope I've managed to convey you the idea that order somehow would be associated not with the energy but with the entropy, so-called entropic order. It happens because of by creating order, you somehow allow more states to exist at the given energy than without having an order. It's genuine and usual. You might think that it may be somehow different from the usual idea of energetic order, where we had that system get stuck in one of the universes because of it's very expensive to pay to go to the other side. Here, the thing that it's very cheap to get energy fluctuation, but it takes almost forever to go from one step ordered state to another ordered state. Roughly speaking, to go from this ordered state to another ordered state, where I switch the all yellow sides to black sides, it costs almost nothing, but it takes infinite, like almost infinite steps to do it. So I first need to turn all my yellow towers. You can imagine like towers, particles residing on top of each other. I need to all set them to 0, and after that, I rebuild it on the other side. It will take infinite amount of steps and infinite time. So we exactly have the same spontaneous symmetry breaking as in the case of the energetic order. So again, we have exactly the same splitting of the Hilbert space, and the tunnel between two walls is suppressed, so it will be again genuine spontaneous symmetry breaking. And I hope I managed to convey that these models are quite interesting, and maybe at some point in the nearest future they could be experimentally realized, and we would have high temperature superconductivity and maybe ski resorts somewhere in the north of Okinawa. Okay, thank you for your attention.
Can you go back to your slides on the checkerboard phase like simulation?
Yes.
The lower, I think the lower temp, like it starts to have some sort of like loops.
Not just some domain voltage, just some tests, some dislocations.
So there's nothing so significant.
Yes,
Okay.
so can wait longer, and longer, and after that you see that will eventually rearrange and it will become perfectly checkable. Just roughly speaking, what's happening here is that I have like two different like seeds of this checkerboard space, and they do not align itself nicely. But after that, one of the seeds will win, and after that will completely become one of the checkerboard.
Any questions, comments?
Yeah. So you're basically studying hidden symmetries in quantum field theory, quantum mechanics, etc. Have you ever considered, or have you ever looked into these kinds of hidden broken symmetries in gravity?
There's no hidden symmetries.
Huh?
There's no hidden symmetries. They're all explicit.
Well, are they? That's the question. You've never looked into this?
All symmetries in these models are explicit. Like here, we have like translational symmetry, right?
That's yes.
So it's just not explicit here.
But if you go back to the 𝐒𝐤𝐭𝐫 to electromagnetism,
Yeah, it's also symmetric
you're breaking a continuous symmetry, right?
in 4D.
Yeah, you're breaking a continuous symmetry, right? That means the initial symmetry of the initial Lagrangian is like a hidden symmetry when you break down around the minimum that you focus on. Does that make sense?
No.
No? Okay,
Because
don't worry.
because how it's different from what Pierre Curie observed. He also broke continuous symmetry here.
Yes, sure. But the initial symmetry before you focus on the minimum is considered a hidden symmetry that does not manifest around the minimum. When they all align in a specific direction, you've lost an explicit symmetry. It's okay. I can explain.
Okay. All symmetries here are explicit. I know from the very beginning.
But it's definitely the terminology that it's an explicit symmetry is not correct. It is called a hidden symmetry. All of these symmetries are called hidden symmetries. In the Weinberg reference you talked about, he discusses it.
Okay.
As to the physical realization of models like this in condensed matter physics, do you see it as being likely in other liquid-solid transitions? And something similar happens in water ice as well, right? Which is why you have the expansion of. So when water solidifies, you have additional entropy due to the motion of the hydrogen atoms, right? And this
Yes.
also is very analogous to what you're talking about.
Yes.
And that has to compete with the additional entropy that comes from the translational motion in the liquid.
Yeah, but after that, in the like in the usual water, right? The entropy of the water state is big of the entropy of the water state, and that's why we have positive Latin heat.
Sorry, could you repeat?
You're talking about Pomeranchuk effect?
Mhm.
Yes, there is like entropy of the liquid state.
Yeah.
It's less than entropy of the solid state, so it's exactly
Right.
the same mechanism.
Yeah.
As here, but I don't know how to realize like experimental some other models that I discussed it.
Mhm.
So I don't know how to realize, for instance, this model or this model. So you can, well, maybe on photonic processor you can do something like that. For some experiments with Brook atom, like the ones that done by looking at Harvard. But maybe it would be interesting to explore whether it's possible or not to realize on some real life experiment.
Online? Good chance. Okay, then let's thank Fedor again.